A series of quick tutorials on what data you can get from Pearson's Crystal data and how to prepare it for later application in data science analysis. First, you start with the search of your relevant class, composition, or specific compounds that you're interested in. This is like your typical output that you have. Obviously, we can get way more information by editing this output and selecting the relevant data field that you want to include by adding and removing them, and also moving them up and down if necessary. We suggest a very specific order of the columns, since it makes it way easier to analyze the data. To be more specific, somewhere in the description we will add a file that will contain only one row and a few columns that start from formula phase, entry prototype, and all other information that could be helpful for us, and it goes all the way down to the entry number. Entry number will be an important one, as it will show you in a quick example soon. So first of all, what kind of data you can get from PCD? The easiest thing to start with is probably just copying the entire column, and Control-C, Control-V brings you all this information into Excel, which you can process later. Obviously, you can save it as a comma-separated variable file, TXT, or any other format you prefer. It's just my personal preference to start working with Excel, as it is very easy to share this data with collaborators and other team members. Also, you probably might want to consider copying the entire CIF file, not copying but extracting it, when you have the export to CIF. In the next tutorial, we will show you how to do it in a faster way. But eventually, what I want to emphasize here, even though you can select many different files and export them at once, there is always a limit of 20 entries per each CIF file. It is very inconvenient when you have one single CIF file with 20 entries in it. That's why it's better just to say one by one file, but we will cover it a little bit later. Also, another helpful information is the info sheet over here, as it contains some additional information. If you prefer their description of atomic environments, it is helpful. But also there's a description of starting materials, and the experimental procedure will tell you more about how that compound was made. For example, at which pressure it is stable, other stability ranges for temperature and pressure as well. So we can copy this information by simply selecting everything here and pasting it in the TXT file. Well, okay, for now, let's just focus only on the table as we get it from PCD. When you copy it and paste in Excel, it looks something like this. So we suggest to organize it in this specific way because it is quite logical. But if you prefer any other order, feel free to do that. Pay attention to the phase formula and phase formula column. These almost look the same, but they have important tags. These tags are HT, M, RT, and any other tags. This indicates basically the conditions for the stability. This is, for example, high temperature phase. Home temperature, room temperature. So very often room temperature is the same as no tag at all. If there is a specific modification at ambient condition, it's indicated like that. So all these tags are quite helpful, and that's why we suggest to copy this column as well. Entry prototype later will become your labels. For example, very typical case when we want to find the structure or predict the structure, we just simply use entry prototype column as the class. And there is a way that you can just convert it like with a software for numerical data, as we need numerical data in a form of matrix. We can't have any other symbols but the numbers. You can just simply select a specific structure type, for example, copper, and eventually, if you don't have a lot of data, you can just Control-H and replace that one with the number. This creates quickly creates for you the format which will be readable by our algorithms later. But anyway, you can skip this point and do it later automatically as well. Space group number on its own, just a selection of symbols. It might be helpful or might not be helpful, but space group number not the simple byte number, might be a helpful descriptor as well, as it is ordered from the least symmetrical to the most symmetrical. Ideally, almost like that. From the least symmetrical to the most symmetrical, it will tell you if your numbers are in the 200s, it's probably a cubic structure. If it is lower, like it is orthorhombic. If it is way lower, like it's probably like even triclinic structure. So this column might be helpful on its own as it is number and provides some information indirectly. It's a proxy for some other symmetry. These columns are in nanometers. I suggest if you are going to care about some anisotropic effects, you can use this data but convert it into angstroms. The same goes for volume, just better to convert it in cubic angstroms instead of cubic nanometers. Now, these are very helpful text over here, which might be used as properties, as variables, but you need to organize them quite in a smart way. So here we have crystal systems, 7 variations in total, and we can provide them a specific numerical tags or specific numerical labels that will help us later on in classification, and also could be used for prediction. For example, we know that cubic is structured crystal system number 7 in this case, so why don't we just substitute cubic with the 7, and we will substitute hexagonal with 6. So this way, as you can see, we are creating quite a logical order, and where we go from the least symmetrical triclinic to the most symmetrical cubic structure, and we have numerical labels. You can do the same thing for lava class and crystal class as well, as this information might be helpful to further down differentiate the structures. Now, for the answers yes and no, we can simply use the same logic here and substitute all yes for 1 and all no's for 0. That is incredibly helpful when you want to deal with some kind of classification for centrosymmetric and non-centrosymmetric structures. So this could be like a very necessary step to do as well. As you can see, the logic here is simple. You extract all the information you can in a row format, paste it in Excel, and do some kind of simple modifications here. I've never found the temperature and pressure very accurate or helpful columns for a simple reason, because we never know if it is a temperature or pressure at the synthesis or for the data collection. Even more, for some crystallographic reports, it by default puts room temperature as a data collection, or even if it was reported at a different temperature, it never mentioned there. And the default information from typical diffractometers is the room temperature. Element count might be helpful, chemistry system might be helpful, but keep in mind that this is ordered alphabetically. I never found it particularly helpful compound classes and structure classes, but they might be useful for some. The structure, if it is calculated or reported experimentally, that might be helpful for us. We prefer something that always says no, so it's always, we know that it was experimental. The level of study is kind of related to the sample form here, but not always. That's why I sometimes suggest to skip the sample column. But level of study will tell you a little bit more about how much you can trust your data, especially in terms of the standard deviation for atomic parameters. Titles might be very helpful in case if you want to quickly search for the properties. As you might search for something like, let's say, conductivity of the compound, a specific property, or if it has some certain magnetism study here, so this might be helpful. Here, not so helpful, a reference as well. In case if you plan to collect your data and then update it, this first release will help you to identify that you don't copy over like the new data. You only copy over the new data, not the old one. Entry number, it's very important because the sieves that we are going to extract will have absolutely the same name, these digits, and .sieve. So we will use this information in order to connect later our data in Excel table with the specific sieve files that we get from the PCD.